Hi students, in the last videos we were just started our topic complex variable here. Complex variable theory. So in this complex variable theory we started with what is a complex number and how it is represented. Okay. So I mentioned if you want to represent a complex number, not like our real numbers are represented on a real axis where you can represent all the 0, 1, 2, 3 or minus 1, minus 2, minus 3. Those are all the fractional numbers like half, 1 by 2, 3 by 2, all the things you can represent it on this real axis. And we recognized if you have a complex number, okay, so we took the example y square plus 1 is equal to 0. If you take the solution of it is y is equal to plus or minus root minus 1, this is nothing but plus or minus I. By definition, root minus 1 is the I, the complex number I. Okay? And if you want to represent it, you cannot do it on a real axis. Then we came to know we need a complex plane. Okay, so a complex plane means here you have two axes. One is our real axis like previous, and there is an imaginary axis. Okay, so this is the real axis according to the real z, and it is an imaginary axis, imaginary z. Okay, and all the numbers you can represent it. It's in a complex plane. This is called a complex plane. So in a complex plane you have an imaginary axis and a real axis. For example, if you want to represent this I, so on the real axis, just like before, you do 1, 2, 3, 4, etc. Then here minus 1, minus 2, minus 3, minus 4, etc. like that. And on the imaginary axis we will put I, 2I, 3I, 4I, etc. And here minus I, minus 2I, minus 3I, etc. like that. Okay. So this is called a complex plane. So if you want to represent any number, whether it is complex or real number, you can do it on this plane. Because if you have a real number like 2, so the point is here. If you have a complex like I, that is here. Minus I, then it is here. Or minus 1, it will be here. Like that, okay? And I told you, you can represent a complex number z in general is x plus iy format. Okay, so whatever may be the number, for example, if you have z is equal to minus 2 plus 3i, then you can represent here. You have to look at the real part. The real part is minus 2, so this is here, and imaginary part is 3i. So the point is, this is the point, like that. Okay? Now we can do some other properties like if you want to, if you have a complex number I. Okay, so if you multiply it with 1 with I, that will give you I. So this is the result. Okay. And now if you multiply this result I into again I, what would be the result? The result is minus 1. So this will come to this point from here to there. Okay. Now again this minus 1 multiplied with I, what would be the result? The result is minus I. So minus I is going to this point. and again this minus I. So whatever the result you got here, multiply with I. What will be the result? The result is plus 1. So this will goes to this point. Okay, and if you do it again, so this will come to this. Okay, so it has certain importance. This we will learn later on. Okay, so we need it. Okay, I will teach you what is the importance of this. Actually, it is a unitary. These are the eigen. Actually, it is a eigen values of your unitary matrix. It will come like this. We will learn it later. So for the time being, we need the basics. So that is a basics. Whatever may be the complex number you have, that you can represent it on this complex plane. Okay. And another thing we studied few of the properties, like if you have a complex number z is equal to x plus x1 plus I y1, and another complex number z2 is equal to x2 plus I y2, like in this fashion. Okay, so you can add it together. So if you add together, that means z3 is equal to z1 plus z2. Then what you have to do? You have to add the real part separately and imaginary part separately. That is x1 plus x2 plus I into y1 plus y2. Whatever may be the complex number, then you can do it like that. Next thing what you learn or we discussed is about the representation. Representation is simple. I told you, if you have a complex number z is equal to minus 3 plus minus 2 plus 3i, then you have to look at the minus 2 units on the real axis and the 3 units on the imaginary axis. Okay, so it will come somewhere here. Okay, so this will give you the mod z. Here if it is I am calling it as z, then mod z, that will give you the magnitude of it. Okay, actually this is simply a point. So from the origin, this length, that is determined by the mod z. Okay, mod z, it is defined for x plus I. Mod z is defined like this. Mod z is equal to square root of x square plus y square. Okay, understand? So this is the way. Now another thing I mentioned, if you have two complex points, for example this is z1, I am calling it as z1, another is here, I am just simply calling z2. In this case, you cannot say z1 is greater than z2 or z2 is greater than z1 like that, but you can say only one thing, that is mod z1 is greater than mod z2, or the magnitude of this you can compare, but the points you cannot compare, or you cannot say this is larger than this one like that. That is not possible. Now after that we checked how to get the resultant of these two. In order to get the resultant of these two, what you have to do, you have to make a parallelepiped and you are just take the diagonal of it. Diagonal will give you the result. Let us check. For example, you have a complex plane like this. This is your real z and this is your imaginary z. Now 1, 2, 3, 4. This is I, 2i, 3i. I am just representing this much only. You can do it for different values. So I am taking my first complex number z1 is equal to 1 plus 3i. Okay, so 1 unit here and 3i unit here. So this is somewhere here. So this is my z1 Now second one is z2. Z2 I am calling 3 plus 2y, 3 plus 2y, where 3 units on the real axis and 2 units on the imaginary axis. So this will be somewhere here. So this is my mod z2 and this is my z1, because this point I call it as z1 and this point I call it as z2. Then you need a resultant of it. So z1 plus z2 I am calling it as z3. This is equal to 4 plus 5y. So that means there will be 4 units on the imaginary real axis and 5 units on the imaginary axis. So it will be 4, then somewhere here 5. Okay. So this will come somewhere here. Okay. So this is your Z3 or this is your mod Z3. Now what you need? You need this point 4 plus 5y without looking like this. Okay. Actually here I added and I just put a point. Instead of doing that, you can directly say, if you know the z1 and z2 in any what you call it, any general point, then what you have to do, you have to make the parallelepiped and take the diagonal. So the diagonal of this will be your z3, okay, and this diagonal will give you the modulus. Okay, you understand? That is another thing we mentioned. Now, what about the polar representation? That also we want to know. The polar representation I already taught. Actually, I made the Euler's formula. What was the Euler's formula? Euler's formula was e raised to I theta is equal to cos theta plus I sin theta. So this was the Euler formula. Okay, and now we will take it to or any one complex point z1. Okay, so that this z1, how do you get it? Z1, the point is z1. Okay, so this after doing this, actually we came to the point is z is equal to r e raised to I theta. Okay? So you can just counter check it, because you have z is equal to x plus iy. Okay, and here I am taking any point. This z is x comma y. This point is x comma y. Okay, x unit on this real axis and y unit on the imaginary axis, and this is making an angle theta. In that situation, what about x? And this I am calling it as r. Okay, then x will be, if you make it like this, what about the x? X is nothing but here x by cos theta is equal to x by r, or x is equal to what will be cos theta is equal to x by r, adjacent side by hypotenuse, x by r, or x is equal to r cos theta. And similarly the y, what about the y? Y is this y by r, sin theta is equal to y by r. So here this will give x is equal to r cos theta and y is equal to x is equal to r cos theta and y is equal to r sin theta. We are just substituting back here, so this will give you r cos theta plus I into r sin theta, or you can take r outside, cos theta plus I sin theta. So this is nothing but, if you just apply the what is called the Euler formula, then you will get z is equal to r e raised to I theta. So this is the representation of the complex number in polar coordinate system, not in Cartesian, in a polar coordinate system. So this is the thing. Now what I am going to do, for example, I have a point z1 at x1 and y1, and another point is z2, so I am calling this r1 as well. Then another point z2, okay, so this is theta 1, y x2 comma y2, or yeah, so this is theta 2. Okay, my points, 2 points are, one is z1 is equal to r1 e raised to I theta 1, and z2 is equal to r2, so this is r2 e raised to I theta 2. So if I multiply it, that is, if I am taking z1 into z2, what will be? Z1 into z2 will give you r1 r2 e raised to I theta 1 e raised to I theta 2, or this is r1 into r2, I am putting it another capital R e raised to I theta 1 plus theta 2, or you can say r e raised to, I am calling this another angle phi, theta 1 plus theta 2, I am calling this phi. So where will be this point? This point will be, you have to get this what is called the amplitude r as r1 into r2, and the angle is phi. Phi is theta 1 plus theta 2. This angle plus this angle, so it will come somewhere here, okay. And r1 into r2, the multiple of this. For example, if this is 2 and this is 3, then it will be 6, isn't it? So this will come somewhere here. So this is my z3, and this angle, this is my angle phi, and this is r. Okay. So this is the way. And these are the things in the last 2 videos I just told you, and I just briefed it for those who didn't understand what I told in the last class. We will go further, okay. So I'll just erase it, and I will give you more and more details about these complex numbers and complex plane. Okay. So in the beginning, these are very easy and simple things, but when we go further and further, we will understand more detailed about this complex variable theory. So now we are not entered into the complex variable theory. Now we just saying the intro or introduction level. And another thing, you may have complex numbers, or you may have complex variables, and you may have complex functions. Okay, this also I mentioned in the last class. I think we can make another video. This is little bit lengthy. So before ending, I would like to say one more thing. If you, I told you, if you have 2 complex numbers z1, z2, then the resultant of it, if you take the modulus of z1 plus modulus of z2, if you add this mod of these two, that is always greater than or equal to mod z1 plus z2. Okay, so this is called a triangular inequality. Okay, triangular inequality. And another thing, I mentioned z is equal to r e raised to I theta, or in the Cartesian coordinate x plus iy. If you want to take the complex conjugate, then what would be z star? This is represented by z star, or sometimes it may be z bar as well. This is equal to r e raised to minus I theta, or in the Cartesian this is x minus I. Okay, these are the things you know very well. Okay, you studied all these things in the math here, subsidiary mathematics. Okay, so these are the things as a primary. And one more thing, when you discuss about this things, the polar coordinates, I told z you can represent it as z is equal to r e raised to I theta. Then the r, that is, this you get it as square root of x square plus y square. And similarly the theta you will get, you can check it in y by x, you can check it at home, okay, how it is coming. These are simply almost similar to our vector calculus. What you do in the vector calculus is the same thing, you get it here also. Okay, yeah, another thing, you have z is equal to x plus I1 and z star is equal to x minus I2. From this one you will get x and y in terms of z and z star. So that is how it is. You just add 2 z plus z star. What would be the result? You will get 2x, isn't it? Z plus z star will give you 2x. So x is equal to z plus z star by 2. And if you subtract it, z minus z star, what will be? You will get 2iy. Z minus z star is equal to 2iy, or y is equal to z minus z star divided by 2r. Okay, so okay, so these are the simple notions. Okay, we will go to next video. Okay, one more point I will just mention and I will finish it. For example, you have a complex point in a complex plane. This is your complex plane, real and imaginary. And you have a point here. This is your z. Z is equal to r e raised to I theta. So this is theta. So this is your z. Z is equal to r e raised to I theta. Now what I am going to do? I will just add theta plus 2 pi. So if I add theta plus 2 pi, what would be the result? So I am adding r e raised to I theta plus 2 pi. So this is here now, and if I add another 2 pi, what will be? This will come back to this point again. Okay, actually here, this point, I have to say based on that point. Actually, yeah. So this point means r e raised to I theta. I am adding e raised to theta plus 2 pi. So this will be again coming back to the same point. Again I am adding another 2 pi. So that means e raised to I 4 pi. Sorry, theta plus 4 pi. So again it will come to the same point, isn't it? If I add 2 pi again and again, 1 2 pi, then 2 2 pi, 3 2 pi, 4 2 pi, like that, you will get the same point. That you can show here as well. So this will be again r e raised to I theta into e raised to I 2 pi. e raised to I 2 pi, what would be the result? You know Euler relation, e raised to I theta is equal to cos theta plus I sin theta. Okay, so I just instead of theta I put 2 pi. So this is 2 pi. So this is 2 pi. Okay, what would be the result? This term becomes 0 and this term become 1. Okay, so e raised to I 2 pi is 1. So this is into 1. Again you will get r e raised to I theta. So you will do it again and again and again, you will end up at the same point. Okay, so in general you can write any complex number, you can rewrite in this form: r e raised to I theta is equal to r e raised to I theta plus 2n pi. Okay, and in this, here you have two things. One is r e raised to theta plus into e raised to I 2n pi, like that. Okay, so here this n takes the number 1, 2, 3 like that. So here n is equal to 0, 1, 2, etc. Okay, this will go like that. Okay, and here the argument of z, means this angle part. Okay, this we call this argument of z. Okay, argument of z, you have a magnitude and an argument. The argument of z is equal to, you have to use small a, argument of z is equal to theta plus 2n pi. So this is the argument of z, and here this value, theta value, this value that we call it as the principal value. Okay, this is called the principal value, and this generally written as the argument of z is equal to capital argument of z plus 2n. So this is actually the basic angle, the initial angle that we call the principal value. So this principal value, this is written as argument of z. Here you have to use capital A. Okay, so if somebody tell you this argument of z, that means this is the theta value. Okay, you have to identify it as the theta value, actual theta value. Okay, after that you are adding by 2 pi, and each 2 pi will take you to the same point on this complex plane. Okay, so what else you need it, and this argument of z is always okay. So this argument of z is always in between. This is always greater than minus pi and less than or equal to pi. Okay, so that you have to keep in mind. But you have to be make sure that this is the principal value. Okay, the argument of z, what you are getting, this one, this total, it is called the argument of z. This argument of z has a principal value and an addition of 2 and pi, and this is written in this way: capital A argument of z plus 2 and pi, and it has the range of value between minus pi and then plus pi. In between you will get any values. Okay, well, it won't go beyond pi.